Okay, we are going to wrap up section 3.2 today. This is actually going to bring a close to chapter 3. There have been lots of terms, lots of templates and interpretations in this particular chapter, and it's important that you are reading back over your notes on a regular basis to kind of commit those to memory. We have been using our calculator to find the least squares regression line. That is typically what we do in AP statistics. However, there are a few formulas on your formula sheet that you need to be comfortable with. We're not from scratch going to be creating a least squares regression line by hand, but we are going to use some of these formulas to help us kind of build the least squares regression line. Okay. Here are two formulas that are actually on your formula sheet. We know we've been using the B to represent the slope, okay? And we know that here's a formula. It's on your formula sheet, so this isn't something that you have to memorize, but you do need to be comfortable with what these variables are representing. So I'm going to help define these for you. Of course, we know that the R is the correlation coefficient, okay? The S sub y would be the standard deviation of the y coordinates, and then the S sub x would be the standard deviation of just the x coordinates. So I suppose if you had your x's in L1 and your y values in L2 and you ran one variable stat on L1, whatever the standard deviation was for that, that would be your standard deviation of the x's. And then if you ran a one variable statistic on the L2 column, the y's, whatever the standard deviation came up for L2, that would be the standard deviation of the y coordinates. Okay, so this is the formula that calculates what the slope is of your regression line. Of course, we use a B for that. We know that we use the A for the y-intercept, okay? And the formula for the y-intercept, again, this is on your formula sheet. So the key is understanding what the variables are representing in these formulas, okay? So when you see a y with a bar on it, that means that's the average of the y coordinates. And of course, we know x bar is the average or mean of the x coordinates, okay? So here's an example. It's talking about many people believe that students learn better if they happen to sit closer to the front of the classroom. Does sitting closer actually cause a higher achievement, or do just better students simply choose to sit in the front? To investigate, an AP Stats teacher randomly assigned students to seat locations in his or her classroom for one chapter. At the end of the chapter, he recorded the row number, row 1 was closest to the front, and the test score for each student, okay? So you can see down here, I think here is our scatter plot. There were apparently 7 rows in the classroom, 1 being to the front, 7 being to the back. That is our explanatory variable, and then the y variable, the response variable, is the student's score, okay? It says the least squares regression line was performed on the data, a scatter plot with the regression line added, that's what we have here on the left, and then a residual plot is over here on the right, and then there are some measures from the regression shown underneath here, okay? Now, they don't give us the equation of this line, but that's what we're going to try to use this information to see if we can calculate that, okay? And here's some added measures they give us. They're giving us the mean and the standard deviation of the x coordinates, the row numbers. So there's x bar, there's the standard deviation of the x's. Keep in mind those are things that are needed in order to calculate the slope and the y-intercept. We're also given the mean and standard deviation of the y coordinates, and then they also give us the correlation coefficient. So since they're giving us all that information right here, we should be able to use that information to build what the slope is and what the y-intercept is. So let's start with the slope. Okay, we know that the slope formula, again, this is on the formula sheet, would require us to take the correlation coefficient, that's the negative 0.218 that we were given in the problem. Oops, I'm sorry, shouldn't have written it like that. Okay, and multiply that by the standard deviation of the y's divided by the standard deviation of the x's. If we were to do that, we would discover that the slope would roughly be negative 1.119. Okay, all right, let's go ahead and see if we can work through then the y-intercept. Okay, again, I will draw your attention up here. Here is the formula for that. Okay, so it's going to be the average of the y coordinates minus the slope times the average of the x coordinates. So you can see why we would need to calculate the slope first, because we need to work that in down here into this part of our formula. Okay, so there's the slope, and that's going to get plugged in right there for the b. Okay, so again, these are some figures that they gave us. We're going to use 812 for the average of the y coordinates. We're plugging in negative 1.119 for the b. Be careful, there's a double negative here. And then the average of the x coordinates is 4.022. Okay, if that were all plugged into the calculator, it looks like we would get for our y-intercept 816.5. All right, so we're going to go ahead and build this equation. Y hat equals 816.5 minus 1.119x. I'm going to define x is the row number, and y hat would be the predicted score. Okay, not that bad in terms of having to do it by hand, because they're really giving us all the information we need. And we know we don't need to memorize these formulas. They're provided right there on the formula sheet for us. Okay, all right, so we're going to go ahead and try one more, and then we're just going to talk very briefly about how as the standard deviation of the x's increases or decreases, and same with the y, how that impacts what the correlation is. Okay, so here we have some people think that the behavior of the stock market in January predicts what its behavior would be for the rest of the year. So take the explanatory variable x to be the percent change in a stock market index in January, and the response variable y would be the change in the index for the entire year. We expect a positive correlation between x and y because the change during January contributes to the full year's change. Calculations for the data for an 18-year period gives, and then here we have much of the same data that was given in the other problem. They're asking us to find the equation of the least squares line for predicting the full year change from January change. And again, the whole show your work piece, which is, you just want to kind of show what I showed up here above. Okay, so we want to definitely start with the slope, because the slope plays a role in the y-intercept equation. Okay, you would not, on the AP test, by the way, folks, have to write down these generic formulas first. Immediately substituting them into the formula is completely fine. I am just doing that here just more to help you see why I'm plugging the numbers where I'm plugging them. Okay, so this is my R, the standard deviation of the y. Now keep in mind that is a percent, so you'll need to swing that decimal point 2 places to the left. Okay, that's divided by the standard deviation of the x's, and that would give me a slope of 1.7068. Okay, let me just kind of move that down here. 1.7068. Okay, great. All right, y-intercept. Okay, average of y's times the slope, or minus the slope times the average of the x's. Looks like that's going to be 0.0907 minus 1.7068 times 0.0175 for a y-intercept of 0.06083. I'm going to go ahead and build the equation. Okay, y-intercept plus slope times x. They said that x was the, x is the percent change in stock market index in January. So percent change in January, and this is predicted percent change entire year. Okay, so you're going to see a few problems like that on the homework come up. What I just want to focus on here is what is in this box, okay? And I want you to really think about this formula for R, okay? Because what we're after is we want to see how does the correlation change as these standard deviations change, okay? And so this getting the correlation comes from the fraction standard deviation of the x's divided by standard deviation of the y's, and then times what is the slope, okay? And you'll notice this is basically this formula, but just that formula solved for R, Okay, that's why they would have multiplied by the reciprocal of this fraction. That's why you're seeing the standard deviation of the x is on top and y is on bottom, because it's been rearranged to solve for that r. Okay, I want you to think about a fraction and how the value of a fraction is affected if just the denominator grows. Okay, so let me just give you a quick little example here. If I were to keep the numerator of my fraction the same, but I would make the denominator get larger, look at what happens to the overall value of the fraction. Here this is 1, but as my denominator gets bigger, the overall value of the fraction is actually getting smaller, yes? Okay, see how this is 1, now we're at 0.25, now we're at 0.1, now we're at 0.01. The bigger you make the denominator of a fraction, particularly if the numerator stays stationary, the smaller the value of that fraction is. So if we want to know what happens to the correlation if the denominator of this grows, so if the the spread of your y-coordinate, if that increases, like you have more vertical spread, that's going to cause your correlation to go down. It's going to be weaker, okay? I want you to look at this picture right here. If you have a lot of vertical spread, okay, it's really spread out. That means a linear, like a line of best fit, a linear graph may not fit it quite as well. Okay, it's going to be a weaker correlation if the spread is vertical. But now I want you to think about a fraction. What if I made the denominator of the fraction more stationary, but now I'm going to change the numerators so that these numerators are getting bigger? What's happening to the overall value of these fractions? Well, this is 1, but this is 4. That's 10. Looks like the overall value of a fraction, if I increase the numerator, causes the whole fraction to increase. So if I increase the spread of the x's, the horizontal spread, that causes my correlation to go up and get stronger, okay? As my vertical spread goes down, but my horizontal spread increases, that actually strengthens the correlation. Okay, so I'm going to kind of color code these things here. As the standard deviation of your y variable increases, meaning you get more vertical spread, that causes your correlation to go down and it gets weaker. Okay, but as the standard deviation of your x variable increases and you're getting more horizontal spread, well, now your correlation is getting stronger, and that's because, you know, we can run a line through there and it feels like that's much stronger than having, you know, vertical spread where there's gaps up and down like that. Okay, so that kind of plays a role into this last part here, which is what we're talking about, outliers and influential points. And I apologize about how this line's running through there. That wasn't supposed to be like that. Here's what an outlier is, okay? An outlier is any observation that lies outside the overall pattern of the other observations, okay? It typically would have like a very high residual value. It can be located in the x or the y direction. So if I were to give you a scatter plot like this and then stick a point out here, be very careful. Sometimes people mistake this as an outlier, but if you think of it in terms of maybe how your line of best fit would be, this point, although it is away from the rest of these points, it's still inside, not outside, the overall pattern, and it would have a relatively small residual because it would fall in line with where maybe that regression line would land, okay? Now, if we moved that point, you know, down, well, yeah, maybe down here, then we would be talking more about an outlier, okay? How is that different from what we call an influential point? An influential point is a point that if you were to actually remove that point from your data set, it would markedly change the regression equation, or it would also dramatically change the correlation, okay? Something worth noting, typically your influential points are located on the far left or the far right of your scatter plot in the x direction, Okay, so it would be something that if you removed it, it would really maybe tip the regression line and cause a big change maybe in the slope or in the y-intercept. Okay, so your influential points, just try to remember this, they're located on the far left or far right of the graph. Okay, so any influential points or outliers that are in the far left or far right in the x direction, that will dramatically change your slope. What it does is it pulls the line towards that influential point, okay? And so in pulling it towards it, it's tipping it and causing a change in the slope, okay? Any of these points located on the far left, far right, the x direction, it will cause your correlation and your r-squared value to go down if it's outside of the pattern. But if it's inside of the pattern, it actually strengthens these two values, the r and the r-squared, okay? If you have an outlier in the y direction, so now we're talking about like maybe something way down here, sort of in the middle of the graph, not in the far right, far left, in the y direction, okay, what that does is that changes your y-intercept, because it would take maybe your regression line and now your regression line is shifted down because it's kind of shifted down to account for the fact that that point is down there, okay? That would cause your r and r-squared to go down because that's clearly an outlier outside of the pattern, and it's causing the standard deviation of your residuals to go up because there's more vertical spread. Okay, there's more vertical spread there. So we're just going to look a few of these examples at the bottom. We won't do all of these. What we're asked to do here in this example is we want to circle any outliers or influential points, and we want to kind of identify the point we circled. Is it both an outlier and an influential point, or is it just one of those two things? And then we want to state how the equation, either the slope or the y-intercept, as well as the correlation, r and r-squared, would be affected if we were to remove that point, okay? So let's look at scatterplot A. Okay, in scatterplot A, I think we all could say that, you know, this is definitely a point that feels like it's off over by itself, but it does kind of feel like it's in the same pattern of the other points, because if you look at the regression line, it has a very small residual. So I'm going to call that an influential point. I don't think that I would call that an outlier in terms of the regression line. That's what we're kind of looking at when we say outliers, because it's in that same pattern. Okay, but if I were to remove that point, okay, if I were to remove it, remember your influential points, it really impacts the slope. Okay, so if this were removed, what impact would it have on the slope? Okay, well, right now this line is being pulled towards that point. So if this were removed, it would be maybe somehow tipped down slightly more. Okay, I don't know exactly how it would look, but definitely it would cause the slope to go in the opposite direction. It's kind of, think of it as it's like tilted and kind of swinging back and forth there. It's being kind of like a magnet. It's hugging that outlier, or that influential point rather. Okay, now how are r and r-squared being impacted? Well, it depends. If that point is in the pattern of the other points, then removing that point would cause your correlation and your coefficient of determination to go down, okay? So that point is actually strengthening it. If it were removed, it would weaken the correlation, okay? All right, let's look at another one here, okay? Here we have, looks like this would be our point. Now that doesn't quite feel like that's in the same general trend and pattern as that other clump of points. Now it is in the far right, so I'm definitely going to call that an influential point, but I'm also going to call it an outlier. Okay, this line is definitely being tipped down towards that. So if I were to remove that point, the slope would definitely increase. It would be tipped up more, okay? This, since it's outside of the pattern, is actually weakening the correlation and the coefficient of determination. So if this were removed, then my correlation would go up. It would be strengthened. Okay, it would definitely be strengthened. Okay, and let's look at example C. This will be our last one that we'll look at. Here we have this point right here. Now, it's not on the far left or right, so I'm not going to call this an influential point. I will call it an outlier, though, okay, because it's kind of in the middle. It's in the middle here, and so anytime it's in the middle and not on the ends, this point is dramatically impacting the y-intercept. So if I were to remove that point, we want to ask ourselves, how do we think that would change this line? Well, that point being there is pulling this line up towards it, like shifting it up. If the point's removed, I think my line's going to be shifted down somewhat, okay? So it's going to cause the y-intercept to go down. That is definitely outside of the pattern of points. So that is weakening the correlation. With that removed, my correlation and coefficient of determination would be increased. And then standard deviation of the residuals. Remember, everybody, the residuals are these vertical distances. Look at that huge vertical distance. That is causing a huge spread in your vertical distances by having that point there. If we remove that, then our spread of our residuals is going to go down. Okay, definitely go down. Okay. All right, we're going to skip those last few there. Okay, and just take a quick look at the back here, just to comment on just a couple of things here. If you were to flip-flop and you were swap out your explanatory variable and your response variable, so like whatever you had as your x, you make that your y, and whatever you had as your y, you flip-flop your L1 and L2, your correlation, your R, is not impacted at all by that. And I think we discussed that before. The R should stay the same. However, you are going to get a different regression equation. Okay, so it's very important that you're careful with what you're using for your X and your Y variables. Okay, one other thing is remember the correlation does not have any units of measurement. So that's why, if you were to flip-flop or change any units, it doesn't impact your R value at all. Okay. Also keep in mind the R, the correlation, it only tells you the direction. And by that, I mean positive or negative. And it only tells you the strength. It does not tell you linear or not linear. Okay. It doesn't tell you that. Okay. And then lastly, the correlation and the least squares regression lines, those are not resistant to outliers that are outside the general pattern of points. Okay. Meaning outliers dramatically affect your correlation and they dramatically change your equation for your least squares regression line. Okay. All right, that is going to bring this to a close. We've got some problems here that you can try in this very last page.